So our plan is to record the session and distribute it among those who are unable to be here. And the objective today was to spend a little bit of time doing a deeper dive, particularly hearing from Zach and Kate and Abby on how we're approaching energy efficiency, because I think that's a piece that we've undersold in communicating. And so we wanted to spend some time doing that today.
Okay.
So that's the objective. I'm going to stop talking and turn it right over because we've got a lot of ground that we can cover. John, feel free to ask questions. And yeah, we'll move forward.
All right. Well, good. I'll go ahead and make sure that I can share my screen and then we can do a brief introduction here. I think Rosie doesn't actually look like I'm able to share this.
I'll enable here, Zach. Give me a sec. Why don't you go ahead and introduce yourselves and I'll get it going.
Sounds good. Yeah, John, it's nice to meet you. I'm Zach Verbeek with KFI Engineers.
Nice
to meet you. So I'm a mechanical engineer by background. We've been working with Abby and her team over the last year on the integrated campus energy study, and this has some excerpts from that. You also likely received a transmittal earlier today that has the final report.
I did, but it came at.
Oh, yeah. You definitely have not had time to review that. Yeah.
Right.
It's a little light reading, John. You should have already done it by now.
Yep.
It's like 4,000 pages. It's not 4,000, but it's a lot.
Well, in Appendix 17, I think there's a particular issue. No, I'm kidding. Obviously, I haven't had time to look at it.
Yep. But this is summarizing some of the items that are within that report. There is a 5-page executive summary at the front end too, if you don't want to peer through all the details of the report.
Right.
So then Kate, introduce yourself.
Yeah, I'm Kate Edwards with KFI Engineers. I'm responsible for energy modeling with KFI. I also have a mechanical background. I've been with KFI for 15 years and worked on the demand side portion of the building energy model for the integrated study.
And John, I think you know pretty much everyone else, but for the purposes of the recording, can everyone just do a really brief intro?
Sure, I can go next. I'm Julia Pfeiffer. I'm the program manager for energy infrastructure renewal. So I'll be implementing the installation of the steam to hot water parts and pieces as we figure out what we're doing. My background is in HVAC, commercial industrial installations.
I'm Abby Bjorklund, Director of Engineering and Utilities for Dartmouth.
And Scott?
Scott Henning, Energy Program Manager with Dartmouth.
And I'm Rosie Kerr, the Director of Sustainability. So take it away, Zach.
Yeah, well, and I'm
John. Go ahead.
No worries. At the MIT Sloan School of Management and at Dartmouth Class of 77. So
Nice to meet you, John. Okay. All right. I think my screen should be up and running. And as Rosie said, yeah, feel free to interrupt at any point through the presentation with any questions. But this is just a general overview of what we'll be going through today. We're going to recap on both Dartmouth's sustainability goals as well as the goals of this specific study. Going to do a deeper dive into the campus demand side modeling, what assumptions went into that, what ECMs have been applied throughout that process, and what the impacts of that have been. Abby also has pulled together some converted building case studies that she's going to walk through. And then we have a truncated technology overview of the supply technologies that have been recommended within the study. I know Rosie had done a presentation utilizing some previous slides that went into a little more depth. We have those in an appendix. If there's any questions, we can touch on those as well. And then lastly, we have a pathway to 2050 showing both the building side and plant side, how those work together to hit the goals. So real quickly to recap, The two charts on the right, the first one is representative through 2021 of Dartmouth's current progress towards the goals. You can see the 2025 line as well as the 2050 targets, and then the current makeup of emission sources on campus. Number 6, fuel oil, still being the largest of the pie. So just recapping, 50% reduction by 2025, scope 1 and 2. There's aging energy infrastructure that can be upgraded along the way, and hitting key efficiency goals as we go through this. We'll talk more to that later. And just as a point of reference, the town of Hanover goals here below. Specific to the study that we've been working on with Abby and her team, first and foremost, as we've gone through this, we've prioritized energy efficiency throughout the process, both on the building side, the distribution side, and the plant side. Because any point that we can increase efficiency has impacts that cascade through the whole system. So it's the number one priority throughout. The study is also targeting to hit the goals that we just walked through on the previous slide. And then as we go through that, the end solution needs to be reliable and scalable, so that we ensure that we're providing the needed energy to campus. Flexibility is important because the future will change, and the plan needs to be able to adapt to that. And then overall, it needs to meet the goals of a sustainable campus. And then the last goal is a relatively, it's a goal that's unique to this study, but it is something that Dartmouth is targeting for looking at a future that can eliminate reliance on combustion on campus in the future. And we'll get into that more later as well. So with that, we're going to move into talking about the demand side model. But before we do that, it would be useful for this group to understand a little bit how we've built these two models. So we've built two models. We have a demand side model that is an 8760 hour calibrated model to the campus, how it operates today. From that, we've added in campus growth, changes in how energy is going to be used on campus, and looked at different ECMs that could be deployed on the building level. That model, after going through and implementing those changes, is able to be fed into a dispatch model that also operates on 8760 hours a year, but also steps through the years all the way through 2050. So we can look at different technologies that may be able to fit in with that, as well as phasing considerations as we go through. The construction side and design side phasing of this project is going to be extremely complex. So it allows that to supplement that. And with that, Kate is going to walk us through the demand side modeling efforts.
So as Zach pointed out, it's important when we're looking at renewable energy solutions that have varying hourly energy production. We want to make sure that we have a good model of the hourly demand so that we can predict the supply of energy and the available energy and match that with the building demand. There are about 120 plus buildings on campus. About 112 of those we have connected to the central plant and included in this model. We had hourly data for 33 buildings, and then we did detailed energy models for 5. This was a good compromise to take the actual usage where it's available, and then also use building modeling of different types of buildings so that we could investigate energy conservation measures and then also compile a good hourly model for the campus. To get the buildings that we don't have data for and didn't model explicitly, We extrapolated based on the building type and similar buildings, and then adjusted those extrapolations by comparing the monthly usage to calibrate it so that the curves were about the same shape, and we got a pretty good calibration. You can see the calibration for the whole campus down below. This extrapolation method got us really pretty close to predicting the monthly energy use for the full campus. But now that we had, once with the calibrated model, and we calibrated to 2018 because it was a good year before pre-COVID, and we had some good data for that. We wanted to be able to predict the future usage of the campus. Getting the building on the consumption reduction, the building consumption reduction is very impactful through the whole campus system. And it's key to achieving the college's goals and prioritized on each of the building renovations. Building usage impacts plant usage and vice versa. And both of these directions have both plant efficiency and building efficiency have limitations individually. The graphic down below uses the blue shapes to represent the building demand, the red to represent the response of utilities to meeting those demands. And you can see the impact that as you reduce plant usage, you have a limit going horizontally, you have a limit going vertically, reducing the building consumption. Together, you can really get a low energy building. We identified the ECMs that were most impactful to the building by looking at building modeling, but then also looking at validated projects that Dartmouth has already completed, looking at the pre and post energy usage. There are a couple different kinds of renovation projects planned for Dartmouth's buildings. There are renovations that include the deep energy retrofits. And deep energy retrofits might include being able to actually reduce or change the HVAC system type and allow for more envelope improvements. Hot water conversions are also planned, and those, while efficient systems are prioritized, those are generally less invasive projects that don't require vacating the full building for as long.
Can I ask a question here? So the vertical axis on this graph is this is for a typical building, right? So this is, each bar is the fractional savings of the current total load. Is that right?
That's correct. This is an example building, one of the ones that we modeled. And it is the savings percent either with an individual ECM or with the combined all of the above. Yeah, different. And so we looked. Go ahead.
The bar on the far right is everything to the left of it together?
Correct. Correct.
So.
And I actually truncated some of this. I left some of the iterations we did for this building out as we went through. There are quite a few iterations. This building actually already had a good portion of the building had already had an LED retrofit. So the LED was
2% more if you do that.
Right.
But tell me why the 39% is much less than the sum of the bars to the left.
There are interactions between the systems. And that was one of the things that we wanted to model them all together as you reduce the building load or increase the ventilation or change the systems interact together. So less load.
So I understand that, but specifically, if you, is this including that when you've reduced the infiltration, exfiltration, you now have to add HRV or ERV to get enough fresh air, and that uses energy and so forth? Or because the energy you need to run an ERV is very tiny compared to the energy you're saving from not having to vent to the exterior hot but stale air in the winter and bring in cold air.
Just this building in particular had the DOAS system, or the dedicated outdoor air system with energy recovery, so like an energy recovery ventilation system, was going to be applied to part of the building. Part of the building had existing energy recovery with a variable air volume system with existing energy recovery. The infiltration change in this one was that the older portions of the building that had not been renovated had very low performing windows, operable windows that were often open when the steam system is on.
Yep.
And so that's where the infiltration, reducing the infiltration and addressing some of the control issues there has a very large impact. This building in particular also has long operating hours, but being able to do some of the controls on it also is very impactful.
So it's a dorm? Is that what you're saying?
No, this one is a portion of the library results.
Oh, okay. No, students are sleeping in the library all the time, so it functions as a dorm.
Yeah.
Effectively, a coffee shop and dorm.
Right.
Got it.
Many of the dorms have, the dorms when going through these, many of them do have the deep energy retrofits. And we are looking at bringing in cooling, to parts of this building as well that don't have, that are not currently cooled.
Right.
But these results on here were on this building. This was somewhat of a unique building, and each of the models that we did had their own unique profile. We had to find a way to extrapolate that to the whole campus as we're going through for doing these energy conservation measures. So that is why we took a combined approach for either we are looking at, for the smaller renovations, the hot water conversions that have are less invasive. For those, we were able to take the calibrated model and adjust the energy usage by a percentage compared to what we were seeing from either the validated actual results or the modeled results for individual impacts. Or if it was a full renovation, we would extrapolate from another building entirely or another model entirely to represent a really full deep energy retrofit.
One of the things that's being done as part of the schematic design or the full designs of the building conversions themselves, as those buildings are getting converted, there are energy models being created for each of those buildings. And the way that this overall campus model has been built, it's been built in such a way that as Abby and her team are converting buildings and getting those energy models done for each, all 112 buildings on campus, those can be input into this model, and this model can be updated from those.
Okay, this is all super helpful. Can I ask another question here? So if we take the 27% bar, which much of that you said is, replacing the double hung windows with good windows. You didn't specify whether they'd be operable in the future, but whatever. So what determined the performance of the windows that you're assuming here?
The calibration process for the building model and site visits, those two combined. When we did site visits, we looked at the condition of the envelope, looked at some of the windows in there, looked at this building has a different build years, so different window types for the different build years. And
So I think I'm asking something a little different, right? So if you're going to replace the windows with better ones, and in the process, you're reducing both the infiltration, exfiltration, and the radiative losses, you have choices. You could spend more and get higher performance windows, or spend less and get lower performance windows. What did you assume? What determined how much you were going to be willing to spend, and therefore the performance you would be getting? And that goes in and determines the 27%.
When we replaced windows in the modeling process, direction from Abby's team was to replace with triple pane low E windows, similar to windows that they've put in some of their other deep energy retrofits. So that was when we were comparing the relative impact of replacing glazing. We were comparing against a very high performance window.
Okay, so the 27% includes an assumption that the college would be spending quite a lot to get close to the very best windows you could get.
Well, I should qualify that this one, the reduced infiltration doesn't necessarily mean a full new window. And actually in these runs that we have shown on this screen, it doesn't include new windows necessarily. We didn't, what the reduced infiltration includes is better control and tightening up, like with storm windows, it could be a similar result. So tightening it up and better control. We know that there is leakage in there based on what we saw in our site visits, and times where a lot of these spaces in these particular areas that we modeled with high infiltration had steam radiators below the windows that had little control, and there were a number of open windows with the steam radiators on, which is what happens when you have, the radiators, there's temperature control issues.
Double hung thermostat, sure, very familiar with that. But I guess, all right, so here's where I'm going, right? Your previous 2x2 matrix, where you lower the load, and then that makes the systems that you need smaller and less expensive. Totally right. That's the core principle of integrated design in this context. But then here, what we're seeing is a certain, and I'm not criticizing, I'm just trying to understand. We have a certain estimated percent reduction in energy use based on some assumption about what is actually done with the windows. And my question is really whether the amount, so whether the amount that's assumed to be cost effective to spend, and therefore what you do to the windows, whether they're all replaced with super high performance, low E, et cetera, windows, or whether you, put in something that's cheaper and then put a storm window over it. Was that determination made by considering the impact on the total system cost, or was it made just on the basis of either a rule of thumb or a standard procedure that's been used in the past, or an assessment of just what's cost effective for the building without considering the impact on the total cost of the entire campus?
I think I'm understanding your question now. And I should clarify that the modeling that we're presenting right here is for the purposes of predicting the total campus energy use as we move into the future. For each individual building with its design, all the design decisions made on the individual building, the buildings have a full energy model that's required as part of the design with life cycle cost analysis. So each of the buildings that undergo either the hot water conversions or the renovations have the engineering team responsible for all of for recommending the full design. They're doing a more detailed energy model rather than relying on extrapolations, and rather than relying on some of the level that we are doing for this full campus study. Now, as each building is going through this process, we can bring in those actual design models. And some of the models, like Dartmouth Hall is one of the ones that we will be presenting, or Abby will be presenting a case study on. That one, we have the full predicted energy model with all the actually implemented design, design that it was actually implemented, that has been incorporated in the whole campus model. It looked like, Rosie, it looked like you were going to say something. I don't want to step over.
I think, John, you're drilling in on a really important point, which is like what sets the bar for how hard we go. Like what, and I think here we have an opportunity. I think the guide for this when we get into a building is our high performance building standard. And so that might be a place where you can, where this group can think about how would we set a goal that tighten that down, right? Because every time we do a building, we're making decisions about, do we put in this window that costs $400 or this window that costs $2,000, and what's the performance of that over time? I also think that, when we look at this at the macro level, we thought about what are the impacts on energy efficiency? What are the constraints of physics that are going to hold us back or improve our speed or whatever? And then what are the costs and how are those going to add up? And so part of the reason there's a renovations bullet here and a hot water conversions bullet is that we can't renovate every building in the first 5 years, right? So we have to have a phased approach to some of the deeper energy retrofits that would involve things like insulation, for example, or ripping out mechanical ventilation, versus the buildings we're going to do hot water conversions on, where we can change the low-hanging fruit systems and then put that on list for deep energy retrofit as we get to that building in its priority order.
So that's helpful. And maybe I'm just being very dense here, but I'm still confused. So let me give you a simple example. And I know the whole campus is more complex than this, but in my house where I am right now, when we did our deep energy retrofit, 1928 structure, very leaky, terrible, we could have looked at how much to spend on the new windows just from the point of view of what's the cost of the new windows compared to the energy saving, thinking just about that. And this is the typical way almost all weatherization assistance programs in the United States work, right? And what they always show is insulation is NPV positive, let's do that. Patching up obvious holes and tightening the envelope, it's positive, let's do that. Windows are not NPV positive, we're not going to do much there. We'll just bring them up to code, or the stretch code that we have in Massachusetts. That's the wrong way to do it, of course, because by putting in better windows than that analysis would have indicated here, I lower my peak as well as average load a lot. And then the size of the heat pumps that I need, because I completely got rid of my natural gas, goes down and their cost is lower. And if I don't count that, now that's not linear, of course, but if I don't count the reduction in the peak capacity of my heating system that arises because I spend more on windows than the building level analysis would indicate, I'm leaving money on the table. I'm not doing a whole system analysis. And so what I'm trying to understand is when I see that 27% number, it has to imply a certain kind of window, a certain amount of everything else that's being done to reduce infiltration, et cetera. And what were the cost calculations that went into determining how much of each of those things to do and how much to spend? And I'm not yet hearing an answer I can really understand. I'm sorry to say, maybe that's on me, but.
No, John, it's a good question. And there's a number of items that have gone into the decision matrix of, which buildings are getting full window replacements and which aren't in this current model. As Kate and Rosie were both saying, all of the buildings at some point on campus will be going through a deep energy retrofit. It's just a question of, what is physically possible to do in the time that it needs to be done in.
Yeah, this isn't really about phasing.
Yep.
This is really not about phasing. I completely understand the phasing issue. It's
So-
about how much am I going to spend? And I understand there's diminishing returns. We have laws of physics, right? I
Yep.
spend more on the next best window. It's going to get me less energy savings than at the beginning. I get that, but it's not flat. And I'm trying to understand, and maybe it's this energy standard Rosie's referring to, which maybe needs to be tightened because it probably wasn't based on the whole system cost benefit story.
And we're going to get into the whole system benefit in a little bit, going through the overall reductions that we're seeing. But the phasing is important to the conversation because of how it has been modeled within this current system. For buildings that are slotted for a complete renovation, for instance, in the current plan, those are receiving, triple pane low E windows as a part of that. For buildings that are slotted for hot water conversion and there isn't ample time in the near term to execute that level of work or re-insulating the entire building, those level of deep energy retrofits from a time constraint standpoint are not currently included in this model. Doesn't mean that it won't be done eventually, but to be realistic about what we should be assuming as we're sizing the systems for the energy transition on campus, making sure that there is enough system capacity to be able to serve the different types of systems on campus, we have to make those assumptions based on what can be constructed. Now, longer term, as we look further out, those windows could be replaced. But right now, some of the governing principles on which buildings are getting full window replacements and which aren't is driven by real world time constraints. Would that be a kind of a correct summary, Rosie and Abby?
Yeah, I think, John, what you're getting at here is that a whole systems approach yields benefits because you think about the individual building choices differently. If you're thinking about the whole system and where when you squeeze the balloon, it's going to bulge somewhere else, or the opposite, right? I think the opposite here. Like if you invest more, you save more. Left hand invests more, right hand saves more.
Yeah, if the analysis is done at the building level, we're going to be doing much less to lower the peak and average load of that building than is warranted, because we'll be ignoring the reduction in the costs for providing the energy for heating and cooling.
I think Kate really hit on this here. This is a high level study, but if you look at the example of Dartmouth Hall, this analysis that you're talking about was done. So when they looked at, do we insulate the walls or not, they also looked at, well, what does that do to the size of the heating equipment? And what is the difference in cost? And then what's the life cycle analysis?
Well, I think we should move on. And Scott, thank you for that. I think it would be useful to see some of those case studies and whatever else is coming, because we're already at 4:00. But okay, so
Okay.
yeah.
Well, I do appreciate questions and do interrupt with more questions as they come, but
Well, don't worry.
okay. Well, so now I do want to complicate things a little bit with energy conservation measures, and that is the addition of adding ventilation to bring buildings that were constructed under previous codes up to current standards. So we are assuming that Dartmouth will bring up all of the buildings all the buildings will be brought up to the current ASHRAE 62 standards for mechanical ventilation. We're also assuming that there will be cooling added to dorms and to academic buildings. Some of those buildings have existing window air conditioner systems or standalone systems at the building level, and those will also be transitioned onto the central campus chilled water system. Looking at the chart on the left, there are some bars to indicate the relative impact of these different competing forces. So Adding ventilation increases heating. That heating is mitigated by the assumption that adding ventilation will always be accompanied with added heat recovery. So that's mitigated somewhat. Adding cooling obviously increases the cooling bar, although the size of those bars is compared to the baseline cooling, central chilled water cooling. It's not a 31% of the total campus energy, it's 31% of the previous central chilled water load. So it is a smaller increase than it appears in those bars. Overall, with the effect of ventilation cooling and ECMs together, those there are interactions that result in increasing chilled water use, but also reducing heat use overall.
It's just a competing force with ECMs that we have included in the modeling efforts.
Now, you tighten your buildings enough, you've got to have active HRV or ERV, and that uses power and so forth. And you're adding cooling that you didn't have before or was done. So, but is that bar for the net of removing the existing window units that are in place in some buildings?
It would be removing local cooling units that were relying on electricity previously, that would instead rely on central chilled water. So it's changing some of the source of that. So this
Okay,
is
so the blue bar is chilled water.
chilled water.
Yeah, okay, and electricity. Okay, got it. Okay, yeah, this is helpful and seems basically standard.
So right, they're competing forces. But then if we go to the other force that we're working on is the addition of square footage to campus. So in this model, all of the new construction is assumed to be high performance buildings, and they will be the majority of the currently planned construction. It is either academic, residential, or combined learning living space, combined use. And you can see the build years planned in the left chart, along with their impact on the total campus energy use or total utility use by chilled water, electricity, or heating. On the right, you can see that the plan is to have all of the campus square footage impacted by this plan. The majority of the impact will be on renovating or doing the hot water conversions for existing buildings. The yellow portions on those bars indicate new construction area. And again, all new construction will be high performance building.
So for new construction, the plan is, a high performance standard.
Mm-hmm.
Have you all looked at, zero net or passive?
Yes, they have. I guess I should let Abby speak to that, but I think the plan is for net zero on new construction. Is that correct? At least on some of the projects?
Well, of the ones that are on this, the only one that we've actually been starting to design is the Lime Road housing. And yes, for those, they are being designed to net zero.
Great. I mean, I would think that unless it's a lab building or something like that, all new construction ought to be either passive or net zero standard. So there's no incremental impact on the load that's needed even as the campus grows.
Yeah, and there's some nuances to that we'll get into later, and how that's where you draw your system boundary on those buildings. But
Sure.
We'll get into that a little bit later, but agreed.
And Rosie, just to confirm, and Abby, is that something that is in the plan, or
What?
net zero or passive house or passive building standard for all the new construction, unless it's, some lab type.
You mean, is that in our high performance standards? Or?
Yeah, is that the plan for all, and the standard that all the new construction will be held to?
Not. I would say we don't have that written into it. I think what you'll actually, when we get to the case studies, we'll kind of go through what we have in our high performance building policy now.
John, that's why I think that's
I
such a
don't know
good.
if you've looked at that document online.
Haven't had time.
Yeah, but that's one, it's a document that Rosie and Scott and I were all on a committee that drafted this back in 2016, and it's in need of a refresh. So
yeah,
and that's a place again where we can formalize those standards that in some cases we're applying by de facto internal, policy, but there is no stated policy, and I think that's a thing that we can change.
Always good to turn those norms into stated policies, right? We've had this issue at MIT. I know we're recording this, so I can't go into too much detail, but it makes a difference whether you have a standard that is official and everybody's feet are held to the fire on that, or it's our goal, it's what we've done in the past, but here's a reason why we don't really have to do that on this project.
That leads to variability, and that's a thing we've experienced in the past, John, that you know this because buildings, Dartmouth building stock well enough, that there are buildings that were built in the past to a high energy efficiency standard, and there were buildings that were not at the same time. Yep. So that's where a standard really comes into play. And Abby's done a good job of reminding everybody there's this guide, and we need to change the settings on that guide.
A provost, a dean, a department chair comes along and says, yeah, I'm totally behind your high standard, but this is an emergency. We have to do it immediately, and we can't afford to take extra time or spend extra money to do what you think is the right thing. And
sure,
that should just be ruled out by policy. Provosts should plan ahead. That's their job.
Yep.
So if we move on to some of our building load forecasting, these charts show the anticipated, even with the anticipated square footage growth, that there is an anticipated reduction in both electricity use and heating use at the building level. Now this is building demand information here, and there is an increase in the chilled water. But that is the key there is that the heating and electricity are expected to be reduced even with the increase in campus square footage.
Yeah, so that's great to see. I guess the kinds of questions that I've been asking, but also the rest of the committee, when we reviewed this in our last meeting, there were small breakout groups, and independently, essentially every one of those breakout groups said, well, looking at this is great, but we could do more. The sense was that despite the careful analysis that you all have done, that the standards that you were asked to meet could be tighter, and that there could be additional, even given the standards you were asked to analyze, additional reductions over and above what you're seeing here.
And I think we will address that as we walk through. We have sort of a sequence that we want to walk through about looking at the energy use intensities of the buildings, and then also combining that with the plant focus. I think if we go to the next slide, this shows the distribution of energy use intensity across campus buildings. Not all the buildings are listed on the axis because of space constraints, but the blue bars on the left show today's energy use intensity, and this is as measured at the building level, the incoming chilled water, steam, and electricity going into the building level. The average the weighted average by square footage, total energy at the campus divided by square footage of the total campus is about 103 kBtu per square foot. And this now energy use intensity is a measure that is used typically to assess, it's kBtu, thousands of BTUs per square foot of building. On the right, the planned after at least the planned deep renovations and plus the hot water conversions that will be completed at 2035, we're showing a reduction from the campus average from 103 down to 85. Again, this is looking at the building level demand, and this will step through a little bit into it warrants further discussion about the energy use intensity as a measure for the campus. And so I'll turn it back to Zach to step through that a little bit, and then we'll get back to addressing really some of the measures on campus that are impacting.
Yeah, and this kind of ties back into the net zero building standards as well. And I mentioned earlier, it depends on where you draw the system boundary a bit. So this figure is an example of a traditional system, either with a single building arrangement or a district system arrangement. So within a single building arrangement, everything is at the building. There's no central plant. Your plant is actually within the building. So you might have boilers and chillers supplying hot water or steam to your building HVAC system. And your EUI within this building is calculated by the incoming fuel, the incoming electricity over the square footage.
Yep.
When you go down to a district system, the way a building EUI is calculated, it's still everything within the red box. But what we're seeing now is only the chilled water energy coming in, the hot water steam energy coming in, and the electricity coming in. So in a traditional system, this actually will show a more favorable building EUI than a single building, because it's not accounting for distribution inefficiencies or inefficiencies in the plant. And when we move towards an energy conversion, say again with the single building conversion example, if we're including electrification of that building, putting in heat pumps, maybe we have some solar thermal or some solar PV, we are effectively reducing everything within this red boundary, and now we're just looking at incoming electricity. And when we're specifically looking at conversions on the heating side, from moving from a traditional boiler to heat pumps, the coefficient of performance, and John, I'm sure you're aware of what that is, but for those who may be listening to the recording, coefficient of performance is a way of measuring an efficiency of a heat pump. And since heat pumps are moving heat rather than creating heat, it equates to being able to provide 4 times the amount of, if you have a COP of say 4, you're able to provide 4 times the amount of heating to a system for every unit of electricity you put into it. So it seems like you're getting 400% efficiency. In reality, you're moving heat, so that's not the case. But from the metrics that we care about, it is the case. So if we're looking at going from a conventional boiler that's say 80% efficient, and we convert to a heat pump with a COP of 4, that's an 80% energy reduction on the system.
This is super helpful. And just for context, the top is what I did to my house. Deep energy retrofit, dramatically lowered average and peak load, got rid of the natural gas altogether, solar PV on the roof, heat pumps for HVAC and heat pump hot water, and spent a little more than the individual analysis would indicate. And the consequence is seven full years of performance data later, we've made 40% more energy than we use with zero fossil fuel. And I have no electric bill, no heating bill, and the electric utility owes me $5,300, which means I'm going to be able to charge and run 2 electric vehicles just on my annual surplus.
John, I think that, sorry.
Go ahead. No, go ahead.
I think that the schematic shows that what we're trying to do is push that kind of thinking into the campus level. So when you get to the bottom, you're sort of taking the whole campus and wrapping your arms around it. And that enables us to do the same kind of cost benefit that you were doing.
Right. And so the bottom one is what we did when we built our new management building, which I was co-chair of the building committee for that. So we made the building much more efficient than code required. It was, all these design decisions were made in the 2005 period. You can do much better for much less today, of course. And it ends up using 70% less energy for heating and cooling than comparable buildings. It's a classroom office building with a big kitchen. And because we lowered the peak load so much, the design spec was 50%, the reality was 70%. But that meant that MIT, which provides steam and chilled water, didn't have to grow our capacity, even though we didn't convert to heat pumps at the campus level, and we didn't convert, we don't have solar thermal. It was the same old system. It's now being changed, right? Same kinds of things as in your plan here and as Dartmouth is doing. Low temperature, medium temperature, hot water instead of steam, et cetera, et cetera. But just by lowering the peak load of the building, we saved $1.9 million in avoided capital cost for steam and chiller capacity. And the net of all of that was, in a pretty careful post-audit, that the net present value of what we did in the building, which cost more than what code required, was positive 9 million and something, almost $10 million at MIT's actual cost of capital. So that's the system level analysis that I want to make sure is happening, so that when you go back to that original chart we spent so much time on, that the 27% or whatever it is not being selected on the basis of what's cost effective at the building level, but what's cost effective at the system level.
Yep. Yeah, and agreed. And, as we were looking at, there's a lot that goes into decisions of what can be done now and what can be done later. And and entirely agree. Every BTU that you can reduce at the building, it cascades throughout the system. I think we're in agreement there.
Yeah, and that was your original slide showing the bottom right having much greater impact when you do both, right?
Yep. So as we look at this, right, I mean, just like we, talk about how this would be equivalent to what you've done in your house, the credit for the technology changes that are done, right? What your limits are within the building when you remove the major energy production centers from the building. You can do everything you can to the envelope. You can do everything within lighting systems. You can put in ultra efficient HVAC systems. But those large swings in efficiency, between a boiler and a heat pump of, an 80% reduction, that's being housed within the plant. So
you still might put solar PV on those roofs that can handle it and aren't shaded and so forth. But,
for sure. Yep.
Yeah,
Exactly. Yep. So as we look at a comparison, this chart is a comparison of building level EUI. Again, that's just heat, energy going into the building, and campus level EUI. You can see the difference. And as I was talking about, with a conventional system, which is currently what Dartmouth has, it hurts the campus level EUI because you have those inefficiencies in that, and the building's not getting penalized for it in the way the system boundaries are drawn. And then the equation flips as the equipment is changed out on the plant side. So what's shown here overall for a campus, overall campus impact is nearly 75% reduction in energy use on campus, which is a significant impact to the campus overall. One other note that, you know, we've talked a fair bit about phasing and, you know, the decisions that are being made now versus decisions that maybe would be made later. You'll notice that, you know, this building EUI is flat beyond 2035. This is the date after which any of the current planned renovations or currently planned building, new building construction ends within the model. You know, there aren't any plans to stop at 2035, but that is the information that, you know, has been assumed within the modeling effort so far. Right? This could very well continue to decrease over time as schedules allow, and buildings that only received a hot water conversion could be gone back to later and receive a deep energy retrofit as schedules allow.
Right.
One of the other things that we have a responsibility to do within this overall study is ensure that whatever is forecasted on the plant side has some level of conservatism to make sure that the campus has the energy it needs to function, you know, in the future. So
of course, I mean, that's standard and good practice. And, you know, I just described how we actually, you know, we planned for 50% based on our energy modeling. We got 70%.
Yeah. Yep. It's a great example. So one EUI, just because of that system boundary, can be a bit tricky to use. Kate has another metric that she wanted to walk through briefly that kind of removes that, you know, just looking purely at carbon emissions per square foot. And Kate, I'll turn it back over to you.
Yeah, so this is great. What's the assumption going forward, Kate, about the carbon intensity of the grid?
That's a good question. So this does use the, Dartmouth has a consultant that has looked deeply into the planned energy impact of the grid, the pounds per kWh produced. This modeling does include the utility forecast reduction of the grid.
Okay.
And John, we can pull that up towards the end as well. I think we have an
So if you're using the utilities forecast, it's almost certainly too pessimistic compared to what's possible and perhaps even likely.
Yes. In fact, you know, it's been updated recently as well. Just some of the near-term projects have been slightly delayed. So we've updated it for that, just to be conservative in the near term for the near-term goals.
Right.
And so this using carbon emissions instead of energy use intensity does let us compare apples to apples, because we can look at what fuel is going in to generate the electricity on the benchmarking side or on the campus side. It's looking at a combination of site generated electricity plus any purchased electricity that would come from the grid. But so when we look at that, both benchmarking data and the data from these predictions for the campus include both scope 1 and scope 2 emissions. So Energy Star publishes some benchmarking data based on the CBEX data, the Commercial Building Energy Consumption Survey, that's looks at the existing stock of buildings across the campus, and then you can tailor that to your zip code and look at in the proper
So they adjust it for your heating degree days, basically.
They do. So one of the limitations of it, though, is that it does not include that database. The Energy Star database does not include all building types. So they don't include some of the, especially the laboratory and science building types.
Sure.
So we pulled an academic building type out of the Energy Star database to look at that for comparison, and compared it with Dartmouth Hall. So now the median Energy Star building would have 14.1 pounds per square foot of carbon emissions. Dartmouth Hall at this point is 10.3 right now.
Yeah. So, I mean, I think that's a useful point of comparison, but honestly, the Energy Star median or whatever the distribution, wherever in the distribution you want to go, it's not best practice. It's not what's possible or even cost effectively what's possible when you take a whole systems look. So
that's true. And we did look at the future by looking at a predicted for a much lower energy building out of the Energy Star database. Future, we're looking at the 3.5 pounds per square foot. And with the future, with the campus, with the campus plant renovations included, it looks like just over 1 pound per square foot for an academic building. Now, for the full campus, that includes those high energy users, the science buildings, the labs, the medical buildings, and everything, the current campus is higher than the current academic building for the climate zone. But post renovation, post decarbonization plan, the entire campus average is lower than what would be predicted for the Energy Star benchmark for an academic building.
Mm-hmm.
So I think the carbon is a better, cleaner comparison.
Oh, I totally agree. I mean, what matters to the climate is total emissions and total emissions, not even per square foot, but over the whole campus, which is going to grow as you've indicated.
Yep.
But this is a much better metric than EUI. And but I guess so that's terrific. My view of the overall targets that you were given, right, is they're not strong enough, right? It's not net zero by 2050. It's some
80% reduction.
80%, right? Thank you, Abby. And my view of this is that's not Dartmouth's share. That's not the science-based target that Dartmouth ought to be aiming at. And it's also not going to be an economically good decision because it's very likely that as climate change continues to make things a lot worse, the price on carbon emissions, whether it's an actual price or regulatory constraints, is going to go up a lot more than what people think it's going to do. So, for example, estimates of the social cost of carbon have steadily risen over the past 20 years because we've learned more about how the climate works, and the news is never good. And the climate is actually showing us that it's more fragile and there's more harm right now today. So I think what's going to happen is those standards, due to regulatory issues or economic issues or social pressure from stakeholders, are going to have to tighten. And we're going to have to actually not go to just 80% lower, but zero. And so we need to think about how this metric can be, so it can fall steeper and all the way down to zero by 20.
I think that's a great point, John. And I think one of the things that's exciting about this moment is that we have an opportunity to shape that. And particularly this group, the ad hoc, or no longer the ad hoc, the energy working group does.
And I think another point, and we may have more on this later in the presentation, but the opportunity cost of carbon today, mitigating more carbon today, going as quickly as possible, even if we only get part of the way there, if we get there part of the way there quickly, it will have a greater impact today than.
Totally right. This is so, Zach, this is a hugely important point that a lot of people don't yet understand. Everybody knows there's a time value of money, right? That you'd rather have $1 today than $1 in 2050. But there's a time value of carbon too, because a ton of emissions reduction today is worth a lot more than a ton in 2050, because every day that those emissions are in the atmosphere from today forward warms the climate. And that's not a
Time value of
trivial-
carbon is maybe more urgent than the time value of money.
I think that's possible. I mean, economists will say, well, it depends on the discount rate, but the risk of ruin if we don't mitigate dramatically on the global level is very high. So exactly what you said, I totally agree. The faster and more deeply that curve, that blue curve falls, the better it is for the climate. And so ultimately it's got to go to zero, but
Yep.
the speed of the decline matters too. And it's great to see in this plan that it falls steeply. You go from 25 to 10 by 2030. And
Yep.
that's great to see. I think we need to be thinking about how to have it go all the way to zero, which I think is inevitable for what we need to do. And to the extent we can, have it fall even faster to get there.
I do think that one of this is one of the results, the quick decline in carbon is one of the results of Dartmouth's prioritizing deep renovations, but also having hot water conversions that are coming quickly, even though the deep cuts might follow later in the next past 2035.
Great.
All right. Well, that brings us into case studies. So Abby, we'll turn it over to you.
Okay. So this is kind of a summary of that Dartmouth High Performance Building Policy document that I was talking about that we drafted back in 2016. Policy is only as good as how it actually gets implemented. And that's always a struggle, as everybody's been talking about. But the way the policy is written, it applies to any capital projects over $3 million. It could be for new buildings or renovations to existing buildings. It requires that we do energy modeling and that the design team in Dartmouth jointly sets a EUI goal, is the way it's written right now, for the renovated or new building. It requires a life cycle cost analysis of ECMs. By life cycle meaning that it's not just a simple payback. It's not just looking at energy costs. It's looking at O&M. It's looking at capital costs. So all of those things wrapped together on bringing everything to a present value. We also, in the current policy, require LEED certification for projects over $10 million. And
At what level, Abby?
I was reading it over, and I don't think we actually set a level in that document. One thing, but we do set that a minimum energy target of 36% below code. Now, when we wrote this, I think we were in the LEED version 3. Now we're into LEED version 4. So this is a pretty big, target, actually, 36% below code. But we have been meeting that, and here's a list of, some of the projects that have been impacted to date by this high performance building policy. And, to be honest, a lot of the ECMs don't really go through a cost benefit analysis. We just say we want new windows. We want them to be triple glazed and low E. We want to, have our systems be as low energy as possible. And so, not everything goes through the scrutiny of a cost benefit analysis, because we're just basically saying to the designers, we want this to design it to be as low energy as possible.
Yeah. Great.
So next slide. So Dartmouth Hall, which just got dedicated this past week, went through a major renovation, and we added mechanical ventilation where the building didn't have it to provide ASHRAE 62.
So is that an HRV system, ERV? What?
It is a dedicated outdoor air system with heat recovery. So basically the air system is sized just to provide ventilation, and the balance of the heating and cooling requirements are provided by water systems. So that's kind of a general policy that we've been following for HVAC systems too, because heat transfer can happen much more efficiently through water than it can through air. So
Totally.
we're trying to minimize the amount of air and limit it really just to the ventilation. And then where we have to provide supplementary heating or cooling beyond what we're getting from the air system, then we're providing that with water systems.
And the heat recovery on the DOAS system is just sensible, or are you also, is it energy recovery as well?
No, it's a heat wheel. It's sensible and latent.
Great.
So we also have added central air conditioning to the building, where, before we had window units in the building, and a lot of spaces weren't air conditioned. We've put in all new HVAC, new lighting. I mean, the building was basically gutted. We also greatly improved the envelope by insulating, and I'll go into that in a minute. But anyway, the pre-renovation EUI for the building was 61 kBTUs per square foot per year. And even with adding the ventilation and the air conditioning, the new building EUI is predicted to be 41 kBTUs per square foot per year. There was one ECM that I wanted to just highlight that we did go through a life cycle cost analysis on, and this was kind of a struggle for me and Rosie and others to push on, but it was to have the walls insulated. So the design team went through an analysis and modeling, cost estimating. We actually did with the analysis on the walls to determine would it be safe to insulate the windows, the walls, and would it cause damage from
Condensation.
from condensation. So the result was a cost increase of $571,000 to insulate the walls. And from the energy modeling, it would reduce the peak load of the building by 26%, which we did calculate, well, for our future hot water heating systems, how much would that save us on the plant side and the distribution side? So we didn't just look at the impact on the building costs in that cost benefit analysis. So when we went through that process, it did turn out to, and we looked over the life cycle of the insulation, which we thought was reasonable to set it 75 years. So even though, it was like simple payback, more than a 60-year payback, the administration agreed, yes, we should go ahead and insulate these walls, and it still has a positive internal rate of return of over 3% over the 7 years.
And
I
that,
think this building represents a huge victory, even though it's not the biggest building, wasn't the biggest energy user, but it's obviously
the most
iconic.
famous building.
It's very iconic. And from my perspective, John, this was a critical win of systems thinking versus single decision building level thinking, because from a building level perspective, you would have, if you were looking at, payback just at the building level, you would not have insulated this building, which would have been an egregious error.
Wouldn't be worth it, right?
Yeah. And so we were able to make the argument that thinking about this building in its context was critically important. And the fact that senior leadership accepted that argument and moved forward on a $500,000 add to the budget. Doesn't sound big, but my experience has been once you demonstrate that, you're in business.
Yeah.
So that's a
What
really
was-
big shift.
So was the same whole system IRR calculation done to determine, what the windows should be?
Well,
My understanding
we
is they
basically
put
told,
storms on them. Is that
yeah,
correct?
so next slide. Yeah, here's a picture of the building when it was under construction. You can see the spray-on insulation that was applied to the walls.
Yeah.
So the architects and the envelope consultant and the, energy modelers did look at different options for replacing the windows versus refurbishing the windows and adding high-performance storm windows to the building. And the energy performance was almost identical between the two. And they felt that from a architectural point of view that we would be better off restoring the historic windows. And
So does that mean that the sashes were replaced, but the glazing is the same, or just that the sashes, the weight pockets were filled in with insulation and you've now got springs on the windows?
I believe that they still have the weights. I think what they did is they put seals around the windows to seal air infiltration and, to basically cut down on any, on infiltration coming through, because what they found is because Dartmouth has done a good job. Well, first of all, we had storms on these windows for the last 100 years, or I don't know how long, but because those have been well maintained, that those 100-year windows are actually in pretty good shape and that they were worth restoring rather than replacing with new windows.
Interesting. So it's a single glazed double hung window with a high performance storm and
Yeah.
still have the sash weights.
I believe so. I don't know.
I think the effect of the sash weight cavities was reduced by the internal insulation, John, which is not totally typical.
Mhm. Okay, super.
Yeah, you can actually kind of see that on the edges there. Interesting.
And then, we also, as I said, put in dedicated outdoor air systems,
Yep.
High performance terminal units like chilled beams.
Yeah, love chilled beams.
Weights.
We put that into our building and it's great. Saved us a ton of money.
LED lighting. Next slide. So I wanted to go through a case study of a hot water conversion design as well. So in this case, we weren't doing a complete building gut and renovation. For all of the buildings that we're doing hot water conversion designs, as we go into the design process, we are requiring energy modeling and ECM analysis and life cycle cost analysis. Same process basically, that we're talking about for the major renovations. And we're typically, looking at energy efficient HVAC systems, controls improvements, LED lighting conversions. Because the building is not going through a major renovation, we're not doing new wall insulation, but we're doing impactful envelope improvements where needed, like adding roof insulation or infiltration reduction strategies, as Kate was talking about before. So next slide. So this is a case study of a hot water conversion that we did at Steel Hall, and it was really a combination of capital renewal and hot water conversion. We needed to upgrade the aging laboratory air control systems. And by the way, Julia, who I think is on this call, was the project manager for this project, and Scott Henning, who's on this call, was like our lead in-house engineer overseeing the energy study and the design of the improvements. So we had failing steam coils in the air handlers that needed to be replaced. And, we said, well, we know we want to convert our campus to hot water. Let's replace those steam coils with hot water coils instead. So we looked at, doing the hot water conversion for all of the steam coils and steam systems throughout the campus, throughout the building. But also we looked for energy efficiency measures and carbon reduction measures as well. Next slide. So the ECMs that we ended up installing, big one was we did a ventilation risk assessment. You're probably familiar with Steele Hall. It's a chemistry building with a lot of very large ventilation, a lot of 100% outdoor air systems. And so we did a risk assessment to figure out, were there opportunities to reduce airflow in some of those labs, but still maintain safety for the students and professors using those spaces. And that resulted in a 28% airflow reduction. We also looked at heat recovery optimization. It had a runaround heat recovery system that we calculated was only 23% efficient. And by redesigning that system, we were able to bring it up to 58%. It's still a runaround system because it's a lab building. We couldn't do like an enthalpy wheel safely. We also converted the steam heating coils to low temperature systems, and we installed a heat recovery heat pump to generate that low temperature hot water for providing reheat and heating in the building.
Right, so you're saying that that's using the heat rejected by other systems in the building, is that?
Yeah, basically the heat pump is it's actually connected to the chilled water system in the building, and it's providing the reheat in the building.
So what's happening with, I know we're running short on time. I can stay a little longer if need be, but I don't want to impose on anybody else. What's happening with the fume hoods? I assume there's fume hoods here. And are they now variable and can be closed off? I mean, this is basic stuff that MIT has done years ago. Fume hoods used to be open all the time, running all the time, whether anybody was in there or not. It's like, punching out all the windows in my house and then saying, hey, but we insulated the walls. And has that been done? I assume there's fume hoods in this building.
Yeah, I think that was part of this 28% reduction, but I'll let Scott answer that question.
Yeah, we actually didn't have to do too much with the fume hoods. You already had variable volume hoods. The laboratory risk assessment basically found some locations where we could reduce the air changes per hour safely.
Okay, great.
Yeah, and there are, on the third floor, there are some teaching labs that it's a really poor setup, a whole bank of hoods connected to one VAV, and we're able to basically just give the professor an occupied, unoccupied switch, so we can really cut back the airflow there, and they've been good at using it when they're not in there. So
great.
John, one of the things, I'm sure you know this, but labs are one of the very few places where campus users have a high impact, behavior has a high impact. And that's a place we've designed a green labs intervention, but we haven't yet rolled it out, largely because it's really staff intensive. But that's a thing that's very much on our radar as well.
Great.
So next slide. So this project was finished in, I think it was 2018, and we did an M&V process for a year after that to measure what the actual savings was. So huge reduction in steam, 75%. Huge reduction in chill water, 88%, coming from the district systems, and a reduction in electricity, even though we added that heat pump.
Yeah, that's interesting. So I mean, these results are, if I just compare them to our management building, which is not a lab building, but it does have a big kitchen that serves the whole East Campus here. We got 70% reduction in steam and chilled water. You've got more. Now you've done this, more recently than we did. So the technologies available to you are better. We had a 42% reduction in electricity. You've got less, but you added a heat pump system that, we didn't do because we used the central district for everything. So very comparable and better. And to do that in a lab building is pretty terrific.
Yeah. The before EUI was 357,000 BTUs per square foot per year, and after is 134,000. So, this was this was one of our most energy intensive buildings, and we're now in the process of planning a similar project in Burke, which you might have noticed from
Burke is physics, right?
It's also chemistry, actually.
Oh, so chemistry has grown. Okay.
Yeah.
I mean, it's
so,
been a long time since I was in those buildings as a student. So yeah.
Yeah. So
Burke is all chemistry of a very high intensity in terms of chemicals, etc.
Yeah.
Okay.
So anyway, let's move on. I know we're like almost 5 o'clock here. So.
Yep. And if people are good to keep going, I'll jump right in.
I can go a little longer, but I really don't want to impose on other folks.
Sounds good. So this is a truncated overview of the selected energy supply technologies that we're looking at on the Dartmouth campus. This is a general overview of the technologies that were considered throughout the process. We looked at many different heat pump technologies, both on the equipment side or refrigerant side, as well as the energy source side, whether it be conventional ground coupled with vertical wells, aquifer, or we even looked to the river or certain air source. We did look at deep geothermal. With the available technologies today, it's not feasible in this area of the country, but could be potential in the future. We did look at solar PV, and we'll talk a little bit about VPPA later on here. Also looked at 2 different types of solar thermal coupled with seasonal storage. Liquid biofuel is kind of a bridging fuel, and then ultimately backup, and then electric resistance and hydroelectric. As we were looking at those different technologies, competing forces in ultimately what is chosen, but most importantly, they need to be able to supply reliable energy to campus. It gets very cold in Hanover. We need to make sure that the building.
It used to anyway. Now it's not so cold.
That's true. Yeah, we're in St. Paul, Minnesota, so we have about the equivalent weather. But yeah, we had 70-degree weather a few weeks ago.
Yeah, so did we.
Disconcerting. And
so
but
I've
yeah,
actually seen these before. I think we saw these in our overview.
So we can go through quickly. Recap of this is the energy supply makeup of what the current plan includes to get to a combustion-free future. So we have 2 different types of geothermal that are being employed. Thermal energy storage, both diurnal and seasonal, tied to solar thermal, and central heat pumps going out to the systems.
Yeah. So a couple of questions about this. So first of all, I think we've now address this, but when the analysis is done for a steel hall, a future renovation or new construction like a steel hall or Dartmouth hall, every kBTU you can take out of the peak load on the coldest days makes this, whatever it turns out to be, smaller and cheaper. And I'm hoping that that is standard part of the analysis, regardless of the phasing plan, right? I understand the short run, if you just say, well, in the short run, we're going to do this to the building, but there's no change in the central steam system or the hot water, it's still going to be made with number 6 fuel oil. So, but that's not the right way to think about it. You want to think about this is coming and it'll be smaller and cheaper and have a smaller campus footprint and lower maintenance, et cetera, if we can lower the peak load of the buildings even more. And
and we do, we've got a couple of slides on that later that goes into that. So all of that demand side modeling and the way that that is pulled into how these systems are sized.
Yeah. So one other comment about this. So, here in Massachusetts, the state passed a bill this past year that says we want 1 million homes in Massachusetts to be converted to heat pumps, cold climate heat pumps, right? So if you just did that, and we're not on track to meet it, and I've been advising our governor-elect about this along with other folks, but if you just do that and you do what I did here, which is rip out the natural gas completely and you just have heat pumps, although I did much more because all the insulation and better windows and HRV, et cetera, lowers my peak load a lot. Then on the coldest days, the electric demand goes up so much that the utility has to turn on the dirtiest and most expensive gas peakers, and you actually end up with more pollution, carbon and others, than if you allowed some of those people to keep their natural gas, their recent highly efficient natural gas heating system. And on the coldest days, it comes on because those things are over 90% efficient now at the point of combustion, whereas your best gas turbine is less, and then you add T&D losses. So a lot hinges here on whether you need the, carbon emitting biofuel backup for the coldest days.
Yeah.
And I think the goal here ought to be to avoid needing that if at all possible, so we can have a zero combustion system. But, think about the boundary, not just around the whole campus, but including where utility is going to be getting the juice for the coldest days to feed an electric system. And if they're turning on a dirty plant to meet that peak load on January 20th, when it's 10 below zero, but it's complicated. It won't be very many hours per year. And the avoided capital cost of, not needing a biofuel backup is really, really big. So
it's a really good point, John. And I skipped ahead a couple of slides just because you've seen these before. But as we move looking towards what the energy profile is, how it's changing from, this is 2025, not today. So it's actually pulled in some of the conversions already into the math here. But as we move, so the gray here is campus electrical load, and this is hourly. So this is 8760. What's shown is 2 years of data repeated. It's the same year, just twice. And we'll get into why we have that shown in a later slide. But as we look towards, the full build out, the overall impacts, just as you said, right, everything that we're doing, we are reducing the heating peaks on campus, and that has an impact upwards throughout the system. You can see the orange line has dropped. Our blue lines, right, those have increased because we've added a significant amount of
adding the cooling, sure, but that's not a big deal in terms of what it does to the electrical demand.
And we're going to get into a couple of charts after this one that'll show why we're seeing what we're seeing. But you'll notice that, yes, in the winter, inevitably our electrical load has gone up, but we are still
Well, the peaks are
summer
lower,
peak.
but the minimums are higher.
Correct. Yep.
So that's not that worrying, right?
No.
In terms of the concern we have here over 1 million heat pump homes with no natural gas, spiking the grid demand in January. So that's very encouraging.
And actually we have the, so this slide here shows why we're able to do that.
That's
So
because you're going to use some biofuel. So a lot
well,
hinges here.
this is actually no biofuel at all. Biofuel is only there for backup. So what's represented here on this chart, the dark blue is representative geothermal. This is your total heating load, broken up into what's supplying it. So the yellow is a small simultaneous heat pump operation. Blue is geothermal.
Yeah.
The light blue is a type of building energy recover that's modeled at the plant level. And then the red is deployed solar thermal energy from the seasonal storage tanks.
That's the big hot water tank.
Those are the big hot water tanks. And then the orange here is on the secondary axis, or on the primary axis here, is the amount of stored thermal energy in those tanks. So we're building it over the summer months, and then we're deploying it over the winter. And those systems have been sized so that it is possible to get through an entire heating season and then come back and recharge without burning a single BTU of biofuel.
Yeah. So you are just touching zero in the last week of March there, the first year.
Yes. Yeah. And I mean, the systems are, it's designed.
Done a Monte Carlo or whatever to estimate the probability that you won't have enough hot water, or alternatively, how big does the tank have to be to give you whatever percentile you want to have to make sure you don't run out. But this is great. And no biofuel. So then why do we need a biofuel backup in the plan at all?
So, in the instance of, so there's a couple of reasons. One, there is no natural gas to the campus, as you're aware. So it's not that we can have natural gas there for backup. If we were to have an extended electric utility outage, for instance, it's a way to minimize the amount of backup generators that need to be run, which those in themselves are going to be a less efficient thermal delivery method than biofuel.
And then if something goes wrong and your geothermal loop goes offline.
Yep.
But,
or you have a failure in multiple tanks and you are not able to. So we do not think it is advisable to fully remove those assets from the plan just from that resiliency standpoint. It is an asset just like an emergency generator that you hope that you never run. But it's there in case you need it to keep your buildings operational.
Yeah, I understand that. I guess there's a big question about where is that sustainable net zero biofuel coming from? And I think you're talking
That's a big
about
question.
Biodiesel, is that correct?
Yes, and that is an excellent question, and it, where it's sourced from, if it's being sourced from a place that is changing land use to grow that fuel and or grow the beans or whatever is being used, then yeah, that has a negative impact elsewhere.
Because the literature here, and this is an area I do some of my research in, wood bioenergy makes climate change worse between now and at least, until well after 2100, even if the forests are managed sustainably and grow back fully, neither of which is likely. And on the feedstocks for biofuels or other liquid fuels, ethanol, whatever, that are grown from crops or crop residues, fast growing. The land use question you just brought up is a big deal. And I don't know if you know the work of Tim Searchinger at Princeton, but old paper, but he showed that the ethanol mandate we have in the United States makes climate change worse unless you cause global hunger to increase. In other words,
Not a good exchange.
no, to grow the extra corn to make ethanol while still growing as much corn as you were before to make Pepsi and Coke and feed pigs and everything else, you have to use so much more land, and then the fertilizers and other inputs and pesticides and herbicides and the fossil footprint of all of that makes climate change worse. So
this is a question that I think we started talking with Lee about this question, John, and about how best to set up this analysis. But the good news about our biofuel demand is that it's relatively small. And there are some, and this is good news and bad news. There are some small or niche producers that are using waste oil from cooking and a few other low carbon feedstocks.
Yeah.
And so the question is, can we rely on those suppliers? Is that reliable enough for our small volumes? And can we supply our biofuel in a low carbon way? I think this is a critical question. You can't just say biofuel and have that be a good answer.
Right.
Because as you know, there's a big range of
matters a lot. So I guess you need to get all the students to eat more French fries and use all that oil.
We do produce some oil, but not enough.
Yeah, no, I know.
But that said, it is a little bit of we have the possibility of using a boutique product because we're relatively small.
Yeah, and
this
is a place. I'm sorry, Zach, go ahead, please.
Oh, I'm just saying it's an excellent point to be made. There's a need for something, because there will be a need for fuel for generators as well. That again would be only used if they're needed. But yeah, where that is sourced is
so since there's no natural gas, the feedstock for electric power generators is either going to be propane or diesel right now, and both are bad. Diesel is worse. You could potentially have biodiesel for your generators.
Yep.
But so there's a lot going on here, and I think again this reinforces the value of even more aggressive standards for efficiency in all the buildings, new and renovated, because then it reduces the size of the backup biofuel and generators that you would need. And that makes it easier that lowers the total cost of those systems that are only used occasionally. They're mostly insurance. And it also lowers their environmental impact, carbon and particulates, PM 2.5 and other, if you're burning even propane, but also biodiesel, you're making a lot of particulates, and then you got to be careful. One of the main objections to the wood plant from the community was the local ground level air pollution. The climate impact is terrible too, but I was concerned about that, and other people were, but most community people were concerned about the ground level air pollution. It's not nothing.
So this, if you do read any of the report, John, this is the plan that is included within the report. There was a comparative analysis just looking at, what if we reduced the amount of solar thermal and did use biofuel as a peaking source. So there's been some analysis done on that, but it's not the plan that's currently being considered.
Good. So I guess I would be interested in seeing the flip side of what you're just showing here, which is what if there was more solar thermal? What if there was a bigger hot water tank? What if there was, solar PV on roofs that could handle it? And reduce the need for the biofuel backup system size.
So we are installing solar PV on the roofs that can handle it, to really be impactful on the electric side.
Yeah,
We
it's-
really need to look at off campus.
Yeah.
Very large PV systems.
So is there discussion about, buying capacity through a PPA? 'Cause this is
Yeah,
also-
in fact, we're actually, the administration and the board just last week agreed to authorize us to start negotiations with a developer, a solar developer for a VPPA here in New Hampshire. So
Okay.
we're,
This is a fraught area. I'll tell you, and this is public record, MIT made a commitment in its current climate plan, scope 1 and 2 actual net zero by 2050 and net zero by 2026 with offsets. So that's public. And I'm on a committee to figure out what those offsets might be. And it is extremely difficult to come up with offsets that you can credibly stand behind as being additional, verifiable, immediate, and durable, which is the framework that I've created to help people think about what are legitimate offsets. And additionality for PPAs is extremely hard to demonstrate. The academic literature here, because solar and wind are now so cheap, they're cheaper than everything else, basically unsubsidized.
Very hard.
I'm sorry?
It's very hard to demonstrate that additionality given the economics, based on economics.
Yeah, so the literature on this, one study that looked at wind plants found that only less than half of them would not, that were bought with an offset, voluntary carbon market offset process, that over half of them would have been built anyway, just on the basis of the economics.
Sure. So
And-
part of what we've done to try to control for that, John, and I think we talked about this briefly because I got into some of the specifics of the proposed PPA in the last energy working group, I think, is hone in on I think it's very difficult to prove with absolute certainty. It's a correlation causality problem where it's really difficult to show this would not have happened if we hadn't been here. But what
Correct.
we've tried to do is limit the variables. So we've looked at only projects in the New Hampshire grid that have single offtake, that are of a size that Dartmouth can be the single offtake entity, because if you're buying into a project that is utility scale in a big market where Dartmouth is 7% of the offtake or even 30% of the offtake, the project, who's the pivotal additional partner is an even more difficult question to answer.
Yeah, if you weren't there, somebody else would buy that capacity very quickly. That's
Right.
not additional. So,
Right.
Yep. So that's
But these
great.
boutique projects are a little more linear.
Yeah. The other issue, although on the flip side, right, they could bundle local communities and buy.
They
into
could,
that.
but it's a lot harder than getting one single
Yeah.
offtake entity. So it's potentially that,
Okay.
true
So
that the
one
barrier
other
to entry.
One other consideration about this, I don't know what the site is that you're contemplating, but many of these things involve cutting down existing trees. That's a very bad idea. And if it's done, the carbon that's going into the air from cutting down those trees needs to be counted against the savings. And the payoff for that is very, very bad. In Massachusetts, it looks like there will be a legislative proposal to prohibit large solar farms if that would entail cutting down forest. So then you
As
really
you can
have
imagine, Massachusetts is a much more progressive place than New Hampshire in terms of renewable energy.
no comment, but whatever the overall politics in New Hampshire are, Dartmouth should be leading
Sure.
on all of this and using the
Sure.
whole system approach, right? So you can't just say, great, now we've got a 50 megawatt solar farm, but oh yeah, we released X tons of carbon when we cut down these trees and destroyed habitat and created other problems. fragmenting the habitat and maybe soil erosion and, et cetera, and carbon released from the soils over time. So
also to factor in, John, and a thing for you to file away, it's a little bit tangential to the conversation, but because you brought it up, is that we do have some possibility of net benefit with the same kind of detailed calculus. So we own a lot of land. How are we managing that land?
Right.
I don't think Dartmouth has any interest in monetizing or even sort of tracking down the precise carbon benefit of actions, but I think there is a lot of opportunity for us to manage land with carbon as a primary consideration. And we've managed land with sustainability as a consideration, and certainly a primary one, but I think that's different than really prioritizing carbon. So that's a thing for you to file away that I'd be happy to talk about more
great.
in the future.
Terrific.
So, and we'll primarily look at the chart on the left here, but this is looking at annual heating energy over time as laid out by the plan, is showing the transition off of steam as it phases out on campus and as other sources move in. There is, right, within the plan, there is a period as the solar thermal capacity is built out that there is a percentage of campus heating that is being supplied by biofuels until that system is fully built out. But as currently planned, by 2050, nearly 85% is coming from a geothermal, and then that 12.5% that essentially is just carrying the peak load is solar thermal as we move forward there. The
John,
two lines.
another opportunity for this group, the energy working group, is to think about the date. We have a carbon commitment, 80% reduction by 2050. Can we move that closer to us? That came up in our last working group, but I think that that's a real opportunity to accelerate the transition. As we know, the next, we talked about the time value of carbon.
Right.
I think really moving that up is an opportunity.
Yeah, and what we're showing here currently, so the wedge chart here is the actual emissions. So this is fuel emissions, electricity emissions, and then just miscellaneous emissions from campus vehicles, et cetera, other sources.
Well, aren't those all going to be presumptively electrified?
Yes,
That wasn't part of this study.
that wasn't part of this study, but what we've chosen a conservative assumption to ensure that we are doing enough. So we have not taken any credit from the miscellaneous emissions.
Yeah, I think that's right. That's a right.
Yep. So, but yeah, currently this orange line here is the 2050 goal, and currently as planned, that's going to be hit by 2034 as the plan lays out now. As we go through, John, you had asked earlier about the grid emissions assumptions. That these are the assumptions that are included in the analysis. So.
Yeah. And in the real world, as whether it's the RGGI cap is tightened, or there's a carbon price put in, or tighter regulations, I think that's going to have to fall faster. Plus, I think the NEPL folks are too pessimistic on what the market forces are going to be. So our governor-elect is on the record, and many people support this. Of course, that we have to get off of natural gas, fossil gas. It's not natural. Get off of fossil gas and not build new pipelines. And that this is bitterly opposed by the utilities here, so we don't know what's going to happen, but that's what's going to happen, I think. And this will the grid will likely decarbonize faster. But you're doing the right thing. So you use their forecast, of course. Okay, I think you all have been super generous with your time here. We're half an hour beyond what we had planned. I'm so grateful, and I learned a lot. I really appreciate your putting up with all my questions.
Well, they've been great questions, John. Appreciate the feedback.
Great.
For
So
us.
if I can just summarize my takeaways, and y'all don't have to agree, but just so I can put them out there. The way the world is going, I think the target that we need to shoot for here is 0, not 80% reduction, by 2050. Sooner the better. Time value of carbon. Faster we can do that, the better. The importance of the whole system cost evaluation, independent of phasing, so that every kilowatt hour and kBTU per year we can take out of the peak load makes everything else cheaper and easier, whether it's phased in before 2030 or 35 or not, for the ultimate system. Taking a hard look then at the standards and norms that determine what's considered cost effective, and tightening up I forget what you called it, Rosie and Abby, but the standard for new construction.
The high performance building policy. Yeah.
Thank you. Making that even higher performance. That's what I took away as opportunities here that need to be taken very, very seriously. And in that case, I think we do even better and might even cost less. And it's certainly going to get us to net zero faster and in line with what Dartmouth's responsibility is in any science-based framework. So that's my takeaway from this.
Sounds good to me.
Awesome.
Fantastic.